This is page 4. We're going to define the continuous time and discrete time signals. The continuous time signals, we typically use little x to represent this sequence. The important thing to note is the index. T is real. So it means that given a function t, and this is the real number, and if this is 0, and this is function x of t, it means that at every point in t, x of t is defined. So this is a continuous signal. So this is what it means here. Now, here the notation say x of t is a function r to r. This, the first r is talking about this. The second r is talking about this. So x of t can be a real signal, or x of t can be a complex signal. So if this is t, this is the real part of x of t, and we technically can say this is the imaginary part of x of t. So in this example, x of t is a complex number. In the second example here. In our course, we can use both, but typically we'll just use x of t is a real sequence. Now, what about discrete time signal x of n? The difference between the discrete time signal is only on the horizontal axis, n. Here, n belongs to the integer. Here is still x of n. Now, what does n belonging to integer means is that the index n can be only 0, plus 1, plus 2, plus 3, and so on, as well as minus 1, minus 2, minus 3, and so on. Now, then the values of x of n, for example, can be here, can be here, can be here, and so on. But not at any points in between 0 and 1 and 2. That means it is not continuous. So this is the discrete nature of the discrete time signal, is discrete time. The value of x of n itself is still belonging to real, means that x of n is still a real number, or actually can be a complex number. The index, little n here, must be integer. Okay, so this is what we are talking about, the difference between the continuous time and the discrete time signal. We are talking about the horizontal axis being t is real, or n being discrete. Now you might ask, what is the values in between this 0, 1, and 2? And the answer is undefined. Now for this part, we are going to only talk about x of n being n is integer and x of n is typically only a real number. Once in a while, we have a chance to see x of n being a complex sequence as well. Let's give some examples. We have a sequence, and pictorially we can draw a sequence like this. Maybe here is 1, the second one is half, the third one is half to the power of 2, the third one is half to the power of 3, and so on. For example, pictorially we sketch like this. If we give you as an equation, we can say x of n equals to 0.5, which is half to the power of n, and we define the values of n, and can only be positive or equals to 0. And when n is less than 0, it is 0. So now you can see the mapping between the functional description of 1/2 to the power of n as well as a pictorial representation. Note that this sequence is not to scale. Now we can also give you in a tabular form. We'll give you the horizontal axis n as well as its value. So then you map different values of n, gives you different value of x of n. So this is a table form. We can also give you like a list or a sequence form. We say that this is the list of values. But when we give you a list of values, we need to give you exactly where n equals to 0 is. Otherwise, you have no idea where does this sequence, where does this value lies in the sequence. So this is the representation of the discrete time signals in these four forms. Thank you.